alcohols isn't that much of a stretch. All right, so we're recording, so let's get rocking and rolling here and talk about alcohols and phenols. And by now, you should know that an alcohol is when we have a hydroxyl group. We call that an alcohol. And when you have a hydroxyl group on what is essentially a benzene ring, and then you add a hydroxyl on it here, that's a phenol. So alcohols and phenols, and we're going to talk all about those in this chapter. So alcohols possess a hydroxyl group, so you can have a compound like ethanol, which is one of the simplest alcohols. In fact, the simplest alcohol would be methanol. So if you write CH3OH, that's methanol, which is sometimes called wood alcohol, is an old common name that's used for it. And then ethanol sometimes is called grain alcohol. Then you have cyclopentanol. And you can see that hydroxyl groups are very common in naturally occurring compounds. I have a couple of them here. I won't go over those in gross and dirty detail because I won't be asking you a whole lot about that. Anyhow, but you can see that you have an alcohol in cholesterol, and that's why you have the suffix "ol," is because cholesterol is essentially an alcohol. You have geraniol, which is the scent of geranium. So if you like to smell geraniums, it's geraniol. Anyhow, so let's move on from there. Also, you can see that phenols, it says phenols possess a hydroxyl group directly attached to a benzene ring, and it's found in compounds like dopamine. Everybody, I'm sure, is aware of what dopamine is. Also, it's found in THC, which is found in marijuana, of course, and capsaicin, which is a very it's a spicy compound responsible, it says here, for the spicy hot flavor of chili peppers. Anyhow, it's also found in compounds that are found in things like poison ivy and poison oak that cause some irritation on your skin. Anyhow, so phenols and alcohol, so we got that. So let's talk about how would we name an alcohol. And of course, I'm going to ask you some questions that deal with nomenclature, and I've assigned some questions from the book that deal with nomenclature as well. And so let's take a look at the rules. And it says here that alcohols are named using the same procedure we used way back in chapter 4 that we used to name alkanes, just with a few modifications. And that's one of the beautiful things about organic chemistry. If you understand nomenclature of alkanes, alkenes, and alkynes, which we looked at extensively in Organic Chemistry 1, then the nomenclature of alcohols isn't that much of a stretch. So let's take a look. It says, number 1, identify the parent chain. But that parent chain, it has to include the carbon that has the hydroxyl attached to it. In fact, you'll hear me sometimes call that carbon that has the hydroxyl directly attached to it. Sometimes I'll call that the carbonyl carbon. In fact, that word, I don't even think it's used in our textbook, but that's what that carbon is called. Then we identify and name the substituent, things like isopropyl, isobutyl, so on and so forth. Then you assign a locant. So a locant, again, just as a reminder, a locant is just a fancy name for a number. Okay, you assign a locant and a prefix if necessary to each substituent. Give the carbon that the hydroxyl is attached to the lowest number possible. That's the same kind of rule you saw with alkenes, right? You always sought to give the double bond the lowest possible number, or the locant the lowest possible number. Number 4, list the numbered substituents before the parent in alphabetical order. You ignore prefixes except iso, and I should also remind you that besides iso, you have to ignore cyclo, and neo. We don't really see neo a whole heck of a lot in our class, but we do see cyclo from time to time. And then the hydroxyl locant is placed either just before the parent name or just before the all suffix. Like an example would be if you said 6-hexanol or hexan 6-ol, and that's something that we saw with alkenes as well. All right, so let's take a look at some examples. It says identify the parent chain. By now, everybody should be fully aware of what pentane is, just a 5-carbon straight chain alkane or an N-alkane. If you put a hydroxyl on the end, you get what's called pentanol. Another way to describe that would be 1-pentanol. If you take a look at this compound shown right here, you can see that it's got, a couple of possible chains, but the longest chain is the one that's highlighted in red. And if you were to put a hydroxyl on this carbon right here, then we have to, again, find the longest chain that has the carbonyl carbon, or the carbon that is directly attached to the hydroxyl. And so you can't use this chain as the longest chain anymore. Again, the longest chain has to contain that carbonyl carbon. So always keep that in mind. Let's take a look at some other rules here. It says the assigning a locant. So here the bifunctional compound. So bifunctional compound simply means a compound that has more than one functional group in it. So here you can see we have a hydroxyl for our alcohol. We also have a double bond for an alkene. So which is it? Well, I think I told you this at the end of Organic Chemistry 1, that when you have a functional group that has an oxygen in it, and then you have one that doesn't have an oxygen, the oxygen will always take precedence. And so the compound would be described as an alcohol. And that's based off of what's called the order of precedence of functional groups. It's something we don't cover in a lot of detail at all in this class, but I'll just tell you that an alcohol will take precedence over an alkene. So, and if you're like, what do you mean by takes precedence? What I mean is, if you look at this compound, you'd say, okay, I have an alkene and I have an alcohol. Which is it? If I was talking to somebody, would I say this compound is an alcohol, or would I say this compound is an alkene? You would say this is an alcohol. Okay, so the rule is going to apply that we would number the chain so that we give the highest priority functional group the lowest possible number as a locant. Okay, so that's why we would not number it, giving the alkene the lowest possible locant. Anyhow, not a whole lot there. Let's see. So it says the hydroxyl locant is placed either just before the parent name or just before the all suffix. And we saw this rule with alkenes. So we could call this 3-pentanol or pentan-3-ol. I would accept either. Keep in mind your quiz is going to be all multiple choice, so there won't be a whole lot of you scribbling things down anyway. All right. For a cyclic alcohol, just like when you had a cycloalkene, the functional group is, you have to start numbering at the functional group. So this seems reasonable that for a cyclic alcohol, the hydroxyl group is always on carbon 1. And so if we have only one substituent on a ring, like we do in cyclopentanol, we don't call that one cyclopentanol. We just take for granted that it's at 1 carbon and there's no other substituent, so we just call it cyclopentanol. However, you can see in this example, we have a geminal dimethyl over here on carbon 3, and so we have to identify that. We don't have to call it a 1-cyclopentanol. Notice there's no locant there, but we do have to provide a locant for the other substituents. And so this molecule becomes R because we have a stereocenter, R3,3-dimethyl cyclopentanol, like that. Common names for alcohols are also very frequently used, usually for smaller alcohols, unless it's maybe a drug or a natural compound that is well known. But you see here we have isopropyl alcohol. That's an IUPAC, or sorry, that's a common name. Then we have 2-propanol, which is an IUPAC name. There's an even shorter name for this compound, which is isopropanol. In fact, you might hear me say that from time to time, and you can go buy a big jug of basically a solution of isopropanol down at Costco, which is because isopropanol is rubbing alcohol. Then we have tert-butyl alcohol. You see the IUPAC name here, and then we have benzyl alcohol, so phenylmethanol. I'm telling you, I would never call that phenylmethanol. I had a stretch just thinking about it, all right? But benzyl alcohol. So again, common names are very frequently used, and you'll see them used throughout the chapter. In fact, if you think about ethanol, which is the first alcohol that we looked at, that's a common name. Okay, the IUPAC name of ethanol would be ethyl alcohol. Anyhow, something to think about there. All right, let's keep moving on. It says here, like halides, alcohols are often classified by the type of carbon they're attached to. So if our carbonyl carbon, which here they're describing as an alpha carbon, if that alpha carbon is attached to 1, 2, or 3 R groups. If it's only 1, we call it a primary. If it's 2, it's secondary. And if it's 3, it's tertiary. So primary, secondary, and tertiary. And again, the same kind of nomenclature or descriptor that you're used to from alkyl halides. I mean, we spent enough time talking about alkyl halides in chapter 7 that you should all be aware of what primary alkyl halide is, so on and so forth. All right, let's talk more about nomenclature. So it says when the hydroxyl is attached to a benzene ring, we already went over this, that we call it a phenol. And so if you had this compound here, again, you assume that the hydroxyl is on carbon number 1. And so we have a nitro group here, and then we have a chloro here. And you want to number those so that you give them the lowest possible numbers. If I was to go counterclockwise, 1, 2, 3, 4, right, I end up with a 4 chloro, 5, 6, but then I have a 6, right? And the way that they have it numbered which is 2 and 4, are lower numbers. And so that is the correct way to number it. So going like this, 1, 2, 3, 4, like that. Oh, right. And you're going to see that later on in this class, we're going to spend even more time naming aromatic compounds. So let's take a look at some examples. I'm not going to go over all of these. Let's take a look at D. We'll start with that one. So you can see that the parent here, the longest chain, is the 6-membered ring that has a hydroxyl attached to it. So that would be a cyclohexanol. Okay, but we have a stereocenter here. And if I want to identify that stereocenter as R or S, or designate the stereochemistry here, I have my proton in the back. This is going to be my highest priority group. This will be second, and this will be third. And so I'm going counterclockwise. My hydrogen is in the back, so this is an S stereocenter. And I can erase all this, finish now, get that out of my way. So I know that it's an S cyclohexanol. And then I have 4 methyl groups. So I would have tetra. So I have tetramethyl. And they are going to be at carbons 2. They're going to be at carbons 2 and 4, right? I'm going to number going like this: 1, 2, 3, 4. So how would I put all that together? I'm going to have S 2, 2, 4, 4. Remember, I have to put a locant for each substituent, and then tetramethyl cyclohexanol. Cyclohexanol. All right, let's take a look at C. I'm kind of going backwards here. Take a quick gander at C. So C is obviously some kind of phenol. Okay, we have a phenol here. And then we also said, what else? We said that the carbon that has the hydroxyl attached, we assume that that's carbon number 1. And so it doesn't matter if I go clockwise or counterclockwise. There's a plane of symmetry through this molecule that I have drawn here in red. And so no matter what, I'm going to end up with the same locant. So 1, 2, 3, 4, 5, 6, like that. I have 2 ethyl groups, and so I would call this 2,6-diethyl phenol. All right, and I'll let you try B. Of course, you have the solution to that in the solutions manual. It'd be a good practice to see if you can designate the stereochemistry here. Get back on your feet on stereochemistry if you haven't been practicing it over the past few weeks. All right, let's talk about some commercially important alcohols. This is one of those things where I could just sit here and probably ramble on for a while, but we'll go over it kind of quickly here. Methanol, that's the simplest alcohol with a suitable catalyst. About 2 billion gallons of methanol is made industrially every year from carbon dioxide and hydrogen, so it's basically a hydrogenation process. Methanol, however, is poisonous. It does have many uses. Obviously, it's used as a fuel. If you've ever made fondue, usually fondue fuel is nothing more than methanol. And if you've ever tried to light a fondue, a fire with the fondue fuel, you probably noticed that methanol burns essentially with a colorless flame. And that's it's so dangerous. And in fact, you could look up the history of the use of methanol in the Indianapolis 500. It was removed from the Indianapolis 500. I don't remember when, if it was the 60s or the 70s, but there was a horrible accident. Yeah, methanol is also a great solvent, and it's also used in a lot of chemical syntheses. Use it all the time as a synthon or a reagent in different syntheses. Something else I'll point out is that methanol can get you intoxicated. It can get you drunk the same way that ethanol can. However, if you've ever heard of people making, moonshine in a still and then they go blind or something, you've ever heard of that, well, that's from methanol poisoning and can cause blindness. And the antidote, and I'm not 100% sure about this, you might want to fact check me on this, but I think that the antidote for methanol poisoning in humans is ethanol. So something interesting there. Anyhow, ethanol is produced by fermentation, and probably you're fully aware of the uses of ethanol now. It's largely used in fuels, right? It's found in most gasolines now. Anyhow, it has many uses. Human consumption, of course, ethanol suitable for drinking and is heavily taxed. And you've probably heard of denatured ethanol, or maybe you have. If you go to, let's say, Home Depot and you buy some ethanol or ethyl alcohol for a project you might need in your house as a solvent, well, that alcohol is not safe to drink. Okay, they do what's called an azeotrope, where they distill that with poisonous compounds like benzene and toluene, and so that is definitely not fit for human consumption. So just to put that bug in your ear. All right, what else? Isopropanol. It says here isopropanol is rubbing alcohol. Anyhow, it's made from the acid catalyzed hydration of propylene, and propylene, of course, is propene. Isopropanol is poisonous. It's used as an antiseptic, and it has many other uses as well, solvent, so on and so forth. All right. Let's talk about physical properties of alcohols. I know that you've all studied general chemistry, or you wouldn't be listening to me right now. So the hydroxyl of an alcohol has a big effect on its physical properties. Compare the boiling points below. If you look at ethane, ethane is just a simple alkane. So we go from a 2-carbon alkane to a 2-carbon haloalkane. So now we have chloroethane, which is a haloalkane. But what do we have in chloroethane? Chloroethane has a dipole, right? So ethane is only going to experience London forces, nothing else. Whereas here we have a dipole. So not only do we have London forces, but we have dipole-dipole forces. And that's why the boiling point of chloroethane is higher than that of ethane. But then you go to ethanol, wow, and it's way jacked up there, right? So it's out of the ballpark. And the reason why is because of the large dipole, and of course it's due to what else? Hydrogen bonding, right? Hydrogen bonding is the strongest of the intermolecular forces. Of course, this molecule, ethanol, does experience dipole-dipole forces and London forces, but the reason I didn't write them down is because they are not as strong as hydrogen bonding. So I'm just writing the major of the intermolecular forces, and you should be able to represent and understand hydrogen bonding and show the delta plus and the delta minus between the hydrogen and the oxygen. Oxygen is the second most electronegative element on the periodic table. And what is electronegativity? Nothing more than the ability of an atom to pull electron density towards itself in a bond. And so it's delta negative or partially negative, and then you have partial positive, and then you draw the hydrogen bond as a dashed line like is shown here, and you draw it between a lone pair and a hydrogen atom. Okay, so if you were to draw, let's say you threw in another alcohol over here, threw in some lone pairs, right? You would draw something like that, okay? All right, fun stuff. Well, let's move on, and talk about, come on. Where'd that go? Back here. Get that. Yeah, we're over here. All right. What else? Physical properties of alcohols. Alcohols, generally speaking, with less than 3 carbons. It says here 3 carbons or less are going to be miscible with water. Of course, if you have an alcohol with a long hydrophobic region, it is not going to readily mix with water. Like if you were to take 1 octanol, this is 1, 2, 3, 4, 5, 6, 7, 8. Hey, what do you know? This is 1 octanol. If you were to take 1 octanol and mix 1 milliliter of 1 octanol and 1 milliliter of water, you would clearly see 2 phases. Anyhow, what else about physical properties? It says an alcohol's potency is an antibacterial agent. I'll let you read that because I'm never going to ask you about that. The antifungal thing, hexylresorcinol, I probably won't ask you about that either. All right, well, let's get down to brass tacks and talk about the acidity of alcohols and phenols. And I don't think that anything in this section will be a stretch for anybody who remembers pKa's and basicity and acidity. It says here a strong base is required to deprotonate an alcohol. Sodium hydride is often used to generate the corresponding alkoxide. And so you should know what an alkoxide is, and you probably already do. We've seen lots of, alkoxides, which is just you have an R group and then you have an oxygen with a negative charge like that. So if you take ethanol, simply take some ethanol and you treat it with sodium hydride. Sodium hydride is a powder. It's a powder, and it comes as a suspension in oil, and I could talk about that, but I won't bother. But you can see that what's cool about the reaction between sodium hydride and ethanol is that hydride, right, behaves as a base and abstracts that proton. In this proton transfer, you're left over not only with the alkoxide, but what do you get? You get hydrogen gas. And this arrow, what does that mean? That means that it's bubbling out of solution, right? It's going up the smokestack. It's going up into the atmosphere. And so that reaction is not going to be reversible, right? Because of Le Chatelier's principle. It's going to push the equilibrium in this direction as long as you're removing the hydrogen gas. In fact, normally, if you take an alcohol, it's like, let's say you synthesized some SATC alcohol that took you a week to make or something, and then you added sodium hydride to it to deprotonate it, well, you would watch the bubbles. And how do you know when the reaction's done? You don't really even have to follow it by TLC or mass spectrometry or infrared spectroscopy or NMR. You would simply just watch for bubbles, right? That's way easier. Just once the bubbles are done, reaction's over. Move on with life, okay? Another way to make an alkoxide is to take an alcohol and to treat it with a metal like sodium, potassium, or lithium. This works really, really well. And in fact, if you buy, you know how you see this right here, right? How many times have we used this in this class? NaOET. I don't know, 10 billion times probably, right? I'm not even speaking in hyperbole. Anyhow, we've used it many times, sodium methoxide, right? And sodium methoxide on an industrial scale, if you purchase it from a chemical supplier, I'm not 100% sure, but I'm 99% sure that they make it this way. The inconvenience with doing this in the lab, of course, is that you have to mess around with sodium on a small scale, which is just a pain in the neck. Anyhow, let's talk about alkoxides and their basicity. It says here, an alkoxide is the conjugate base of an alcohol. And remember, Aereo, to rationalize the relative acidity of an alcohol. And so what's going to make something acidic? Something is going to be acidic when its conjugate base is stable. And you can see here that the reason why an alcohol, right, the reason why an alcohol is more acidic than an alkane or an amine is why? Because its conjugate base is more stable. And why would that be? Because the negative charge is on a more electronegative element. Of course, I'm repeating things that you've learned in Organic Chemistry 1, but it's always good to think about those things a little bit. And then, of course, if you have a halo acid like HCl or HBr, right, they're going to be even more acidic because the negative charge is even more stable on the halide. Anyhow, we're not talking about halides, but you should understand the rationale here, right? Of course, all students should understand acidity and basicity. ACS loves to ask questions about those, but let's get to the task at hand, which is discussing alcohols. And generally speaking, alcohols have pKa's between 15 and 18. Okay, so between a pK of 15 and a pK of 18. And of course, water falls in there too, right? Water has a pKa of 15.7. All right, well, let's move on and talk about factors that can affect the acidity of alcohols and phenols. And we'll look at a question that deals with this in just a few minutes. It says here, resonance. Phenol is millions of times more acidic than the conjugate base. Phenol is millions of times more acidic because the conjugate base, phenoxide, is resonance stabilized. And so if you compare the difference in acidity between phenol and cyclohexanol, phenol is going to be, what, 10 to the power of, this is 10 to the power of 8 times more acidic than cyclohexanol, right? So that's a lot of orders of magnitude. I don't even know what that number is, of 10 million. Anyhow, and why is that? It's because when we draw the conjugate base of phenol, which is called a phenoxide, we can draw some beautiful resonance structures. They're all shown here, and I know that everybody who's listening to me right now, you're like, Mr. Deon, I could draw those in my sleep. Okay, cool. That's awesome. That makes me really happy. Okay, but you got to understand that what is that resonance? What are those resonance structures? What do they, what's the word I'm looking for? What do they demonstrate? They demonstrate that this negative charge is stabilized, right? It's stabilized, okay? Whereas if you were to draw the conjugate base of cyclohexanol, and you can do that if you want, I mean, we could just draw, we would end up with this, okay? And there's no resonance structures that we can draw, okay? So resonance is the first one. What else? Induction, and this shouldn't be a huge stretch for anybody. What's the whole point of resonance? Was finding a way to stabilize the conjugate base. The same thing applies with induction, okay? If we were to draw the conjugate base of ethanol, which is ethoxide, okay, one of our chestnuts that we love so much, okay? If we were to draw the conjugate base of trichloroethanol, which would be this, okay? Well, what do you know? That you have an inductive effect by these three beautiful electronegative chlorine atoms that help to stabilize that negative charge on the alkoxide like that. Okay, so induction. So we've covered resonance and we've covered induction. What comes next? Let's see here. Solvation effect. So this is something new. So if you're waiting for me to cover Aereo from soup to nuts, atom, resonance, induction, orbital. No, we're not doing that. He just, in the slides, all I was saying is you should be cognizant of that, okay? So we've covered resonance, induction, and now we're going to take a look at what are called solvation effects. And this is something new to you guys. This will be new, but trust me, it's very understandable. And if you look at the difference in acidity between ethanol and tert-butanol, hey, there's a difference, right? Ethanol is 100 times more acidic, right? 10 to the power of 2, if my math is correct. This is 100 times more acidic. Well, why the heck would that be? Look, I can't use resonance as my argument, and I can't use induction. Well, it says here it's based on something called solvation effects. It says the more poorly solvated a conjugate base, the less stable it is and the less acidic its conjugate acid is, okay? So the difference is based on the solvation of the conjugate base. So let's take a look at what the heck that looks like, and it's right here for you. Okay, so you have your ethoxide. So this is one conjugate base, and here's the other conjugate base. So it's just comparing the two. Well, what's acidity based off of? The stability of the conjugate base. Well, you can see how ethoxide, when it's formed in the solvent, wow, you can get more solvent molecules. I mean, here it's only one more, but you get the idea. You can get more solvent molecules around that negative charge to stabilize it, right? T-butoxide, I mean, it's got this big old tert-butyl group, and if you're thinking, well, Mr. Deon, that doesn't look very big, well, try making a model. Okay, make a model from a molecular model kit, and you will see there is a big difference between these two R groups. And so we can have, or we get basically end up with less solvent molecules surrounding that negative charge, stabilizing that negative charge, and that's the reason why ethanol is going to be more acidic than tert-butanol. Kind of cool, huh? All right. Well, let's try one here. Excuse me. I'm going to just throw it out there to my students. Let's take a look at A. Who could tell me which one of these would be, what's it saying here? Identify one that's more acidic. So who could tell me which one of these would be more acidic? Would it be the primary alcohol or the tertiary alcohol? Does anybody have an idea which one of these would be more acidic? Okay. Sorry, my chat seems to be acting up. Yeah. So Winona and Chris both say the primary, and I think you're right. Okay. It's going to be the primary. So it's the primary, and it's based on solvation effects. Okay. The rationale is shown right here. This is a primary alcohol, and this is a tertiary alcohol. A primary alcohol is going to be more acidic, and it's based on solvation effects. All right, if you have your microphone unmuted, if you could mute it, that would be great. Let's take a look at the next one. We have these two really interesting compounds, phenol, of course, and then we have this one here, which is what, 2, 3, 4, 5, 6 pentachlorophenol. Anyhow, kind of a fun compound. But we have these two compounds. Who could tell me which one of these would be more acidic? The one with all the chlorines or simple phenol? Anybody get an idea about this one? Which one would be more acidic? Think about the rules that we just looked at. Somebody says the second one. All right. Somebody says the one with the Cl, the chlorinated one. Yeah, it's the chlorinated one, and I'll tell you why. Well, actually, let me ask you guys. Could anybody give me a one-word answer as to why this will be more acidic? What did you? Yeah, thank you. Exactly. Induction. Exactly. So, chlorinated is more acidic due to induction. Or if you wanted to put inductive effects, right? But you have all of these dipoles yanking that negative charge towards the chlorines, which would help to stabilize the negative charge. I'll help you out with C. Let's do that one pretty quickly. So in C, okay, this one here is going to be more acidic. And I'm going to wait for somebody to type in a one-word answer as to why this is more acidic. Based on what? More acidic based on resonance. Exactly. I'll put here since resonance. Okay. So Mauricio asked, doesn't resonance trump induction? But the thing is, Mauricio, if you look at these examples here, okay, they both have the same number of resonance structures. They have the exact same resonance structures. And so you can't use that to differentiate between, as a way to explain the difference between the relative acidities. Let's move on. We'll take a look at the last one. Obviously, a phenol is more acidic than terbutanol, and that is based on resonance. So nothing new there. So we'll just put here resonance. Like you're driving by in a car and you have to answer the question, you know, just drive by resonance out the window. Okay, let's talk about how would you make an alcohol. So I'm sure somebody's like, this sounds interesting. How would you make some alcohol? How would you make some home brew on a Friday night and drink it on a Sunday morning? Well, that's not what we're going to talk about. Anyhow, there's all manner of ways to prepare alcohols. It says here that alcohols can be synthesized from alkyl halides via substitution. If you're thinking, hey, this looks kind of familiar, didn't we learn this in 3101? Absolutely we did, okay? And if you're wondering where we did this, this would be content from chapter 7. We said if we take a primary alcohol and we hit it with a strong nucleophile, strong base, strong nucleophile, like hydroxide, we would get a little bit of E2, but the majority would be SN2. What else? If you take a tertiary alkyl halide and you hit it with a weak base, weak nucleophile, so that's a solvolysis reaction, you can make a tertiary alcohol like that. So again, this would be chapter 7, and I'm not going to reteach organic chemistry 1 because I don't have time to do that. Let's see here. Let's move on and take a look at these reactions. Again, these are all review. Okay, you can even see where you would find all of these reactions. Oops, over here, 9.4, 9.5, 9.6. And in fact, we even looked at these reactions last week, so I won't spend a ton of time on this. But it says here alcohols can be synthesized from an alkene. You can do just treat it with a dilute acid, so dilute sulfuric acid, and you could write sulfuric acid. And if you're like, well, I like to write H3O+, that's totally fine with me. You could use oxymercuration, demercuration, and you remember why you use these conditions is to avoid carbocation rearrangements. What else? You got hydroboration oxidation. That's an anti-Markovnikov addition, and we went over that in gross and dirty detail last week. So let's move on from there. So you're like, hey, this is cool. I already know some neat ways to make alcohols. And so again, I'm going to go over this pretty quickly because these are all reactions that we would have learned. Every single reaction on this slide is something that we've already covered, and I want to move on to things that are brand new. It says here, identify the reagents that you would use to accomplish each of the following transformations. Well, here we're starting with a tertiary alkyl halide, and we want to make a tertiary alcohol. So that's just a solvolysis reaction. And so we would simply put the molecule in water, and that's an SN1 reaction. The next one we just looked at, these first two really. We start with a primary alkyl halide. We want to make a primary alcohol, so we would use, sodium hydroxide to do that, and that's an SN2 reaction. What else? This next one is a Markovnikov addition of water across a double bond. We don't have any carbocation rearrangements to worry about. If you're on H3O+ or dilute sulfuric acid, that works with this guy. What's next? The next one is an anti-Markovnikov addition, so borane, the old borane and CHF, and then in the second step you treat it with hydrogen peroxide and sodium hydroxide. And the last one's the only one that's a little bit quote-unquote tricky, and I shouldn't even use that word. Could anybody tell me what you would do in this last one here before we really get into new material? It's like Rocky and Bullwinkle, something completely new. I'm wondering if anybody has an idea. Yeah, so John says mercuric acetate, right? He's saying oxymercuration, demercuration. So essentially what he's saying is use these conditions that I had right back here, okay? So mercuric acetate and water followed by sodium borohydride, and we can scribble those in. So One would be mercuric acetate, so mercuric acetate and water. And then in step 2, you treat it with sodium borohydride, which we're going to see again in a few seconds. But just so that we're on the same page, and this is the last bit of review that I'll do on, carbocations rearranging. But what would happen if you were to take that alkene, right, and you were to treat it with H3O plus, okay? And you should always be on top of your mechanism like this. We would end up with a proton transfer, and we would produce this carbocation like that. And now you can see that this carbocation is clearly going to rearrange because it is a secondary carbocation. And when it rearranges, we end up producing this compound where we now have a tertiary, right? We have a tertiary carbocation. And so we need to avoid carbocation rearrangement. All right. Well, that's enough about that. Now let's get into the really fun stuff, what you came here for, which is learning some brand new, exciting reactions. Okay, it says here, a third method to prepare alcohols is by the reduction of a carbonyl. What is a carbonyl? A carbonyl is when you have a carbon doubly bound to an oxygen. And if you're thinking, well, isn't that a ketone? Anytime you have a carbon doubly bound to an oxygen like that, that's a carbonyl. So we see carbonyls in things like aldehydes and ketones and carboxylic acids, right, and amides. Okay, so we see carbonyls and esters in all kinds of different functional groups. Okay, but whenever you see a carbon doubly bound to an oxygen, we call that a carbonyl. So reductions involve a change in oxidation state. Oh, and if you're like, oh, this sounds like general chemistry to me. Oxidation oxidation state is a method. It should be here. Is a method of electron bookkeeping. Recall how we used formal charge as a method of electron bookkeeping. I know everybody that's listening to me is very good at formal charge by now. You know where to put the formal charges on oxygens and halogens, right? Says each atom is assigned half of the electron it is sharing with another atom. What is the formal charge on carbon and methanol? Anyhow, let me show you. And I'm going to slow down just for a second here and kind of give you a little preamble to this slide. So if you think all the way back to when you took General Chemistry 1, you would have spent a lot of time talking about oxidation states, right? You talked about the oxidation state of oxygen and nitrogen. So you learned about nitrides and phosphides and, chromium, chromium 6, and what else? You learned about copper 1 and copper 2, iron 3, so on and so forth. We could, blab about that all day. But if you think about it, you never discussed the oxidation state of carbon. It never came up in a conversation. So that was left for this class, okay? Now, it says here to determine the oxidation state of an atom, imagine the electrons in a bond as a lone pair on the more electronegative atom. So let me show you what I mean. And first, I'm going to address the left-hand side because everybody that's listening to me, even if you've forgotten the formula, you all know how to calculate formal charge, right? Formal charge, I taught you, was valence electrons, the number of valence electrons, subtract sticks, right? Subtract dots. What, sticks and dots? Yeah. So if you take this compound here, which is methanol, why do we not put a charge on the carbon? Because it has a charge of 0. Why is there no charge on the oxygen? It has a charge of 0, right? A formal charge of 0 and a formal charge of 0. Where did that come from? Well, carbon has 4 valence electrons and it has 4 sticks. Done. Okay? So that's formal charge. So I'm not going to go over that. Now, this side here is all new. Okay? This is completely new to you unless you read the chapter. Actually, I'm sure you all did. But it says here, you treat all bonds as ionic. You're like, what? Yes, you treat them as ionic, and you break them heterolytically, right? In the formal charge, we broke them homolytically, but here we're going to break them heterolytically. So you're going to have to remember the electronegativities of a few elements like hydrogen. Hydrogen is 2.1, carbon is 2.5. Nitrogen is 3.0, oxygen is 3.5. I'm sure you all have these memorized anyway. Fluorine, everybody, that one is 4. So if we look at this molecule, okay, if we look at methanol, now it's saying you got to break all of these bonds heterolytically, all 4 of them. Well, let's look at the first one, the bond between carbon and oxygen. Who's more electronegative? Oxygen. So oxygen takes all of those electrons. right? And that's why carbon is left with no electrons here, okay? If you look at the other three bonds, well, looky, all three of them are carbon-hydrogen bonds, so they're all identical. Carbon is more electronegative than hydrogen, and so the two electrons in the bond, carbon takes all of them. So now when we calculate the oxidation state right here, the oxidation state is going to be equal to valence electrons subtract all of the electrons, okay? So we have 1, 2, 3, 4, 5, 6, okay? So subtract the electrons that are on there, so minus electrons, and you could write electrons left over, or maybe David Klein has a better way to describe it than I do. And so the oxidation state of the carbon here is -2. Okay, so that's the oxidation state, not formal charge. Remember, we're talking about two different things. Don't start comparing apples and oranges. And so if you do that same exercise, okay, and you calculate the oxidation states of carbon in all of these compounds here, I see that carbon has a very wide range of oxidation states, and that's why you left it out in Gen Chem 1, right? You didn't really talk about the oxidation state of carbon because it can be -4, -3, -2, -1, 0, +1, +2, +3, +4. You're like, is it just mean, Jerry, or is that a lot of oxidation states? Yes, it absolutely is. Let's take a look at another example, okay, just for fun, and I don't know if I have room to do that. But here's the carbon of interest in this molecule called formic acid. Okay, if you were to break all those bonds, heterolytically, the oxygen has two lone pairs, but it's going to take all of the electrons from the double bond, right? We have another oxygen here, right? That's going to take the other electrons, and then you have a hydrogen and a carbon, and the carbon is going to take the two electrons. So that means that carbon is left over with what? Two measly electrons. So carbon has 4 valence electrons, subtract the 2 that are left over, and you're left with +2. Okay, so that is how you calculate oxidation state. All right, so in an oxidation reaction, and again, this is probably not a stretch to anybody here, carbon's oxidation state is going to increase in an oxidation reaction, and in a reduction reaction, carbon's oxidation state is going to be decreased. And I will probably ask you a question, on the next quiz, what is the oxidation state of carbon in this molecule or something like that. It's all you got to do is calculate the oxidation state. So all of that was just a preamble to what is a reduction of a carbonyl. Okay, so it says converting a carbonyl to an alcohol requires a reducing agent. And if you want to calculate the oxidation states here, I've already gone over this, but the oxidation state of the carbon here is +2, and here it's 0, okay? And so we gained electrons, right? That carbon gained electrons, and you might remember GR, which is gain electrons, is what? Reduced. And so this is a reduction reaction when you convert a carbonyl into an alcohol. So here we have a ketone being converted into a secondary alcohol. It says, of course, you can't have oxidation without reduction, and so the reducing agent is oxidized in the process while the substrate is reduced, okay? The reduction of the carbonyl group overall results in the addition of 2 hydrogen atoms across a pi bond. And so you might be, seeing into the future here with a crystal ball and saying, well, if it's 2 hydrogens, might this involve H2? And the answer is it can. And it says here there are 3 reducing agents that can be used. So the first one is catalytic hydrogenation. So if you had a compound like this is called cyclohexanone, and if you were to take cyclohexanone and just treat it with, and if you're like, this looks so familiar to me, H2, palladium, platinum, or nickel, hell yeah. Okay, you just take that, and basically what you're doing is you're adding 2 hydrogens, right? You're adding a hydrogen on here, and you're adding a hydrogen here, and you're breaking the double bond, and that's what the reduction is, okay? So addition of hydrogens. And here's catalytic hydrogenation. I took this picture off the internet, but what's inside all of these balloons? This is nothing more than H2 gas in all of these. And then the catalyst, these, I know we've talked about these literally hundreds of times, palladium, platinum, or nickel, is that those metals always come absorbed onto carbon. Carbon is black, and so that's why they all have that black color, is because it's like a suspension, anyhow, being stirred. Anyhow, you get the idea here. But it says here, this method is rarely used because sometimes you have to turn up the temperature. You're messing around with hydrogen. It's like, I don't know. Anyhow, and let me show you. I'm going to kind of get ahead of ourselves here a little bit. And let me show you, there's a problem, okay? If you had this compound here, so now you've got an alkene and a ketone in the same molecule. If you were to take that and do this, you would end up not only reducing the alcohol, but you'd also perform a hydrogenation on a double bond. So is there a way that you could simply reduce the ketone without touching the double bond? And the answer is yes. Okay, there is a way to do that, and I'll show you right now. It says here, sodium borohydride. Hey, and you're like, hey, I know that from oxymercuration, demercuration. This is just a bottle of sodium borohydride to show you what it looks like. It's just a white solid. It says here, sodium borohydride is a common reducing agent for aldehydes and ketones. And you got to remember that it's used for aldehydes and ketones. It's not used for amines, amines. It's not used for amides, esters, carboxylic acids, other functional groups you haven't learned about, carbamates, I don't know. It's not used for anything except a good old aldehyde, or an aldehyde, or a ketone. That's what you use sodium borohydride for. So here we have a ketone, and we treat that with sodium borohydride, and you have 3 possibilities of solvents. And you notice that they're all polar protic solvents: ethanol, methanol, or water. So we could even write that in here: polar protic. Okay. And if you're like, what's a polar protic solvent? You would go back to chapter 7 and read about that. Okay, so polar protic solvents. And the reason it's so important that you remember that it's a polar protic solvent is because we're going to look at another reducing agent that cannot be used in water. Otherwise, you could end up in a big flaming mess, and I mean a big fire. Okay, so let's talk about the mechanism of this reaction. Now it says here sodium borohydride, and here's the Lewis structure of the borohydride shown right here. They left out the spectator ion, the sodium. But anyhow, it says here that sodium borohydride is a source of hydride, H-, which does a nucleophilic addition to the carbonyl, carbon followed by proton transfer from the solvent. So basically a 2-step process. So you have your sodium borohydride. Again, here's your borohydride anion, and then you draw a curved arrow from a pair of electrons between the boron and the hydrogen. Hydrogen is more electronegative than boron. And then you draw a curved arrow from one of the pi bonds like this, and so we end up with an alkoxide. And then again, we're in water or ethanol or methanol, and so it removes a proton from water or methanol or ethanol to form an alcohol like this. Now, if you're a very astute student, which I know you all are, I know you all love organic chemistry and you're all into mechanisms, and you might be looking at this mechanism being like, where is the boring? Where's the BH3? Well, hey, where's my sodium atom? Where's that? Okay. Well, I'll tell you the God's honest truth that this is a very simplified version of the mechanism of sodium borohydride reduction. In fact, I think there are several things that are not well understood about this mechanism, and it looks very simple here, and it's very plausible, absolutely very plausible. But I'm not going to go any deeper than this mechanism because this is what's provided in our textbook, and it's also what you would need to know for the ACS or a DAT or an MCAT or a PCAT or anything like that. Okay, so this is the mechanism. If you're like, I like this mechanism, it's pretty short, you're absolutely right. Okay, let's just talk about the stereochemical, the stereochemistry of sodium borohydride reduction. Now, the borohydride, right, the hydride is coming in, and since we have an sp2 hybridized carbon here, and it's trigonal planar, that means basically the hydride could attack from either side, and so here you end up with a pair of enantiomers, so a pair of stereoisomers. Here it's enantiomers, what they're showing. I mean, that's probably not a stretch for anybody here. Give me a thumbs up if you follow me so far. I know I've been talking quite a bit. It's 8:51. It feels like 10 minutes to me, but I know it feels like 51 minutes to you. So does everybody follow? You give me a thumbs up, follow me thus far. Yeah, okay, because we're still kind of, getting into just the nuts and bolts here. Well, okay, I got Diego and Sean are giving me the thumbs up. Well, that's the green light, and Lily too. Let's take a look at another reagent, and this reagent here is responsible for probably the biggest accident I've ever seen in a lab. I saw somebody taken out of the lab on a stretcher, and it was for not using lithium aluminum hydride properly. So lithium aluminum hydride is LiAlH4, very commonly used reagent. And if you're like, Mr. Deon, that sounds scary if you saw somebody get really seriously hurt. Yes, I did. And you can see that it's stored even in a metal can, okay? So that's a can that's got a lid like that you got to pop off with a screwdriver or something, just like a paint can. And what's that for? That's to keep the atmosphere the heck out of there, right? Lithium aluminum hydride is very reactive, okay? And what the person that I worked with, what they had done is they had mixed lithium aluminum hydride, which we abbreviate LAH. They mixed it with this compound here, CH3CN. So that's called acetonitrile. And that made a major fire and an explosion. So don't ever do that. Anyhow, so and if you're like, why are you telling me stories about a fire? Okay, the reason why is because lithium aluminum hydride is a two-step process, okay? There's water right here, right? But what did I tell you? If you mix lithium aluminum hydride and water directly, you will get a fire. Yes, the person is okay. They got some third-degree burns and mostly second-degree burns, but the person was okay. I mean, Lily, this was a long time. This is almost probably 20 years ago. So this has been around about the year 2000. But yeah, it was horrible accident. Burned the person's lab coat off. Their pants were burned off. Their shirt was okay because it was made out of cotton. But anyhow, it was a mess. Anyway, where the heck was I? So what I'm saying is this. Now, we're not doing paper quizzes on account of the pandemic, but every once in a while, I'd get a student who would do this. You know, they'd be on the right track, and they'd write LAH and water, right, like that. And I'd be like, whoa, that's a big no-no. You've got to make sure steps are important. And if you're like, well, how can you add water to the reaction with lithium aluminum hydride? Because you add it in a stoichiometric amount. What does that mean? If you started with 1 mole of the aldehyde, you'd add 1 mole of this very carefully, right? And then once the reaction is done, the lithium aluminum hydride is consumed. Then you add water last, okay? All right, LAH and water. So you can reduce an aldehyde, like shown here. You reduce it to a primary alcohol. So let's get into what else can you do with lithium aluminum hydride. But before we do that, we'll compare the two. And the book doesn't go into gross, dirty detail about this. This is something you maybe want to Google or whatever. And I could even ramble on about it for 5 minutes, but I won't bother. It just says here that if you look at the Lewis structures of sodium borohydride, right, NaBH4 and lithium aluminum hydride, they look pretty damn similar to me. They both have a group 1 cation. They both have, you know, aluminum hydride, borohydride, you know, -1 charge, yada, yada, yada. Okay, well, there is a difference between them, okay? And the difference is based off of the 2 cations, okay? It's based off of their Lewis acidity, and it's also based off of the central atom here in the hydride, okay? And that aluminum is more electropositive or is less electronegative than aluminum has an electronegativity of around 1.6, and boron, I think, is 2.0, something like that. Anyhow, so I am never, ever, and you can take me to the bank on this, I will never ask you, like, why is lithium aluminum hydride more reactive? Not going to ask you. All you need to know is that lithium aluminum hydride is much more reactive. But I know that some of my students just can't take my word for that kind of stuff, and they need to quench their thirst for knowledge. So if you want to look that up, be my guest to do that. But again, it will never be, I'll never ask you a question about it. You just need to know this, that LAH is much more reactive than sodium borohydride, much more dangerous. It says here that LAH, or lithium aluminum hydride, is much more reactive. It cannot be used in the presence of a protic solvent. What's a protic solvent? Things like water, ethanol, methanol, right? So H2O, ethanol, methanol, MEOH, etc., isopropanol, whatever. The proton source has to be added after, right? It's the second step, okay? So the first step would be this, to add lithium aluminum hydride, and then the second step would be to add water on it. And looky, I bet you guys are going to like this. The mechanism is virtually identical to the, like, hey, this is the same mechanism, Mr. Deon, that we saw with sodium borohydride. All you did was change one element and change, I don't remember if the last one was a ketone or aldehyde. Anyhow, I digress. Yeah, they're basically the same. And you can kind of assume the same thing that I told you on the sodium borohydride reduction, that I think that this mechanism is not completely, fully understood. And so this is a simplified version of it. And I'm sure that if you were to Google it, there's probably all kinds of, hypotheses out there. You can look at those if you want to, but let's face it, you're learning quite a bit of material here. So let's summarize what's going on. So you remember this chestnut? I brought this up a little while ago. I said, if you were to have a ketone and an alkene in the same damn compound, pardon my language, if you were to take that and just treat it with hydrogenation conditions, so H2 and palladium or platinum and nickel, you would just blow everything to smithereens, right? You not only reduce the alkene, but you reduce the ketone. And that's cool. If that's what you want to do, by all means, go for it. It's even in a good yield, okay? But if you want to selectively reduce just the ketone and leave that alkene intact, you're like, well, maybe you wanted to do a Markovnikov addition of HBr on there. I mean, there's no Markovnikov here because it's symmetrical, but maybe you wanted to add HBr to that, right? Maybe you wanted to do make an epoxide there, right? Well, then you want to leave that intact, and in that case, you would choose either sodium borohydride reduction or lithium aluminum hydride reduction. Now, I'm sure that somebody's out there going, well, which one would I use? And the answer is really either one. And if you're thinking, well, come on, Mr. Deon, I thought you said you wanted us to be efficient, and the first one is 1 step, and the second one is 2 steps. Well, the second step, that's kind of a 2-part answer. The second step, that's actually called a workup. It's not really considered a step. Anyhow, that's sort of beyond the scope of our class, but I'll make it easier for you, okay? The reason why, and this is something I've probably told you a handful of times in this class, all good organic chemists should know a few ways of doing the same reaction. And the reason why is because sometimes you'll be working on a big molecule with many functional groups, and you'll say, okay, I'm going to reduce this ketone. I've got an alkene somewhere else in the molecule. Hey, let me just throw some sodium borohydride. Look, if it was something that had never been tried before, and which is what research is busting the frontiers or exploring the frontiers of science. I wouldn't be taking all of my starting material and just being like, let me throw some sodium borohydride and I'll just be 100% sure that it's going to work. No. A good scientist would say, I'll take 5 milligrams and give it a try, check it by TLC. If I think I have a good yield, then maybe I'll proceed, right? Oh, it didn't work. Hey, what else could I do? Scratch my face here for, maybe some lithium aluminum hydride. Try that. Oh, that didn't work so great either. And so there are many different hydride delivery agents that can be fine-tuned using derivatives with a varying R groups. And so there's all kinds of them out there on the market. Believe me, this guy doesn't know them all. There's many, many different ones that you can buy. It says you can, for these R groups, it's saying they could be alkoxides, cyano groups, big bulky groups. For example, one that I do know that I used quite a bit in industry is called sodium cyanoborohydride. So you replace one of the hydrogens with a cyano group. And what that does is it mitigates the reactivity. In fact, that is very, very good for reducing the carbonyl on an amide. Now, again, that's not even in this chapter. I'm just throwing it out there because I'm sure there's somebody out there who might be thinking, maybe I could develop a new method for carbonyl reduction and make some dough. You probably could. There's such a market for these things. All organic chemists are hungry for new reagents. If you're selling, they're buying, usually. All right, so let's take a look here. And if I had to really distill this section, what I've been talking about for the past probably 10 or 13 minutes, if I could just tell you, if somebody said, Mr. Deon, you got 60 seconds, buddy, teach it. Okay, this is what I would show you. Okay, I would say lithium aluminum hydride is also strong enough to reduce esters and carboxylic acids. Okay, but sodium borohydride is not. Okay, and so the take-home message is that you can use sodium borohydride can only be used to reduce aldehydes and ketones. Lithium aluminum hydride can be used to reduce aldehydes, ketones, carboxylic acids, and esters. Okay? It can be used to reduce just about everything under the sun because it's very strong. Now, instead of just writing, lithium aluminum hydride and water, I think the book usually tends to write excess, and I like to abbreviate it XS. I can't spend all that time writing those other letters. Yes, so what am I thinking of here? So reduction of a carboxylic acid or an ester, that will yield a primary alcohol. It's always going to give you a primary alcohol. Also, reduction of an aldehyde. An aldehyde will also give you a primary alcohol. It's only when you reduce a ketone, and I'm really scribbling a lot on here. If you take a ketone and you treat that with LAH and water, you end up with a secondary alcohol. Okay, so that gives you a secondary alcohol. Anywho, what else? You know, I teach this reaction in nursing chemistry, and we don't ever talk about mechanisms, but I do teach them that not only when you reduce an ester, not only do you get the alcohol, you also end up with the other alcohol coming from this alkoxy portion here too. So I guess that's important for you to know. Let's see here. Take a look at the mechanism for showing here the reduction of an ester. And this is, and if you're like, oh, isn't it just the same thing that we saw for the aldehyde and the ketone? No, not really, not at all, because after you deliver the hydride, you end up with this intermediate here, which is really wacky. It says here that then you lose an alkoxide. And if you're thinking, Mr. Deon, alkoxides aren't good leaving groups, well, you'd be in the right place, okay? And it even addresses that here. It says methoxide is not a good leaving group, but it can be a leaving group here because this intermediate right here is so high energy. Okay, so it is a high enough energy intermediate that you lose the alkoxide, and then you end up with an aldehyde, and then that gets reduced. So there you go. That's the mechanism. And if you think about all the mechanisms we looked at today, they're all pretty similar. All right, well, let's get a little bit of practice. Let's try one of these here. Let's try drawing a mechanism where we show the reduction of an aldehyde or a ketone. Let's just do A for now. Again, you have the solutions to these and the solutions manual. And so let's get some practice drawing our Lewis structure of our lithium aluminum hydride. I'll tell you something I don't like here is they always leave lone pairs out. Anyhow, let's just draw our aluminum hydride. We're going to leave the spectator ion out for now. But since I can delete things, I'll just tell you that the lithium, what it does is it complexes here and it pulls electron density away from this carbon, right? It makes that dipole even stronger. It basically makes that carbon more susceptible to attack by the hydride. Okay, anyhow, again, you don't need to know that. I'm just throwing it out there because my students have inquiring minds. So let's draw some curved arrows. So we'll show our hydride doing the nucleophilic attack. Of course, carbon cannot have 5 bonds. We're going to put a lone pair up there. And so let's draw the intermediate that we get, which is this here. We have 2 hydrogens. I'm just adding that hydrogen in for instructional purposes. Okay. And then what are we going to do next is we're going to extract the proton from water. So this is the second step. We'll draw the Lewis structure of water. Draw a beautiful curved arrow, extract the proton like that, and then we're going to end up with a primary alcohol, right? Because I told you that an aldehyde will produce a primary alcohol. So there we have it. Now, again, I'm leaving out, right here I drew the hydrogens in, here I left them out, right? We know that they're there. We like beautiful, tasty, online structures. Okay, well, that covers section 12.4. I'm going to let you guys try the next one, which is just a sodium borohydride reduction. So you would start by drawing the Lewis structure of the borohydride. You would draw your first curved arrow like a Sioux, so on and so forth, and you would draw the alkoxide. Then you would extract a proton from methanol in that case, which is protonic solvent. Anyhow, well, let's move on to section 12.5, preparation of diols. It says here diols are named using the same method as alcohols, except the E is not dropped from the alkane name, and the suffix diol is thrown on the end. So here we have 1,3-propane diol. What else? We have 1,5-hexane diol. You've probably heard of propylene glycol. I don't know. Did I put the structure of propylene glycol in here? Guess not. Anyhow, you've probably all heard of ethylene glycol, right? Because that's one of the components of most antifreezes. Anyhow, we could draw. Have you guys ever heard of propylene glycol? Anybody heard of it before? Propylene glycol is also used as an antifreeze. So this would be propylene glycol. And when I moved to the United States, I discovered this television show called Forensic Files, and I watched a bunch of the episodes of it with my wife, and I don't know, a while ago. Anyhow, and they always had all kinds of cases where somebody had been poisoned slowly, and then the investigators showed up at the house and started poking around the basement. They're like, "Well, we were looking around and we found, 50 jugs of antifreeze." And the thing is that antifreeze, so ethylene glycol, is very sweet. It's got a really good taste, but it's also deathly poisonous. And so now I think the antifreezes, I believe they have bittering agents added to them so that children won't, get in that, or you can't use it to poison a loved one. That's kind of a oxymoron, isn't it? Anyhow, let's move on and talk about how you would prepare a diol. And you could make it from you could make a diol from the reduction of a diketone. So here we have a beautiful diketone. And we're reducing that using what? Hydrogenation, lithium aluminum hydride, sodium borohydride. Those all work. Hey, we're getting close to the end of the lecture. I bet you guys could use a reaction that you know. Here you go. We throw two reactions that you already know very well at you: anti-dihydroxylation and syn dihydroxylation. So again, if we take a cycloalkene and we treat that with a peroxy acid, right? This is a peroxy acid here. You could write MCPBA, that works. First you make an epoxide, then you pop it open with acid. That's good. Or what else? We said you could do a syn dihydroxylation. We really learned like Avogadro's number of ways to do that. Potassium permanganate and cold sodium hydroxide, osmium tetroxide, and what? Sodium bisulfite, sodium whatever, sodium sulfite, sodium bisulfite. Anyhow, we also learned this way, which is to use a catalytic amount of osmium tetroxide in this co-oxidant, which is N-methylmorpholine N oxide. So hey, two reactions you already know, two beautiful reactions. And I know we only got 5 minutes left, and I will give some time for questions at the end, but I really wanted to get to this section here, which is the Grignard reaction. This is a really important reaction. It's an old reaction, but I guarantee you that somewhere somebody in Colorado right now is firing up a Grignard reaction as part of a research or maybe a synthesis or something, because Grignard reagents are very powerful, used all the time in organic chemistry. Discovered by Victor Grignard. He won the Nobel Prize in 1912 for the discovery of the Grignard reagent. Victor Grignard, a little bit of history about him, and you guys could read this and learn way more than I could teach you off the top of my head, but I know that he was involved in the syntheses of mustard gas in World War I, I believe, and phosgene as well, which were used as, in chemical warfare. Anyhow, enough about that. But, something Dr. Diaz always tells the chemistry majors, and I've probably stolen it and told you say the same thing, is that if you can find a way to make a carbon-carbon bond, an efficacious, reproducible, affordable way to make carbon-carbon bonds in organic chemistry, you, my friend, are headed for the Nobel Prize. You're going to get it, okay? Because, think about all the bonds that we make. We don't make a whole lot of carbon-carbon bonds. In fact, one of the only carbon-carbon bonds that we've really learned in this class is by taking an acetylide or an alkanide, right, from chapter 9, and using that as a nucleophile. So Grignard reagents are often used in the synthesis of alcohols. It says to form a Grignard, you take an alkyl halide, and you can buy all kinds of alkyl halides for very, very cheap from all kinds of chemical suppliers. And then it says here, you treat it with magnesium metal. And you can actually make a Grignard reagent as an undergraduate very easily in the lab. You literally take magnesium metal, and I'm sure everybody that's listening to me has seen magnesium before, or you've probably lit it on fire at some point in your life. Anyhow, if you take magnesium and you just stir it in a solution with an alkyl halide, you can even do the reaction in ether, diethyl ether, and warm it up with the palm of your hand. Like your body temperature and a little friction on the glassware will be enough to warm it up and form a Grignard reagent. And so if you're wondering, well, how in the heck did the magnesium get in between the carbon of the R group and the halogen, the element X? That's beyond the scope of our class, but that's basically called an insertion reaction. And so you can see here that if we were to take bromobenzene and treat that with magnesium, we would call this phenyl magnesium bromide. Okay, and over here you'd call this propyl magnesium chloride. Okay, well, let me tell you, if you worked in a lab, what you would actually say to another person, I mean, you could go up to somebody and say, hey, do you have a bottle of phenyl magnesium bromide that I could borrow? But normally you would just say, can I borrow the phenyl Grignard? And they'll know what you're talking about, right? So Grignard, he's been gone for a long time, but he's still very, very famous in the world of organic chemistry. Anyway, I want to talk about this cool bond here between, and I'm sure somebody's thinking about it already, between a carbon and a metal. Like, well, that's kind of interesting. I get this carbon metal bond. What the heck is that? Okay. Well, if you look at the difference in electronegativity between carbon and magnesium, it's what, 1.2, around 1.2. And so I'm just going to say this out loud. I'm not going to write it down. But if you think back to the difference in electronegativity, we said that if something is between 0.5 and 1.7, then it's polar covalent. So technically this would be a polar bond, like is shown right here. But it's close enough to ionic that it actually has quite a bit of ionic character. And so, in fact, I won't even get you to think about it like this. I'm going to ask you to think about it like this. So we're going to actually think about the carbon involved in that bond as being a carbon anion, or what I call a, excuse me, a carbanion. Okay, so you can treat this like it's got a lone pair here, okay? And then it can act as what? A tasty nucleophile or as a strong base. All right, I know I kind of firehosed quite a few concepts at you, but there was some what I would consider review in there to some degree. So I'm going to go to my application here because I have class in a few seconds here. And where are my students? All right. Well, that was a lot of information. Look, you've all, I think that 90% of you have had me as an instructor before, and that is what it is. But if you haven't had me as an instructor before, I just want to remind you that this class is not an easy class. And if I could give any advice to anybody out there who's like, wow, that was a lot of information, try your best. And I was a student for a long time. I know it's not easy, but try your best to read the book before you come to lecture. That will make the lecture much more digestible, much more relaxing. If you're like, hey, I saw that. Hey, I saw that. Hey, I remember that. And then I can fill in the gaps. If you're like, I didn't understand that. Well, now I do, right? So try your best. Again, I know it's not easy to do, but I would strongly encourage you to do that. All right, well, I'm going to stop the recording now, and I'm going to have to sign off because I have class in a couple seconds.